Good morning, everyone. I hope they all had a nice weekend. I apologize that I can't be there today. I'm going to be out for a few days. But in the meantime, we're going to get going here and move forward. Today you're going to be looking at lesson 20.1.7, which is adding vectors using components. Essentially, on Friday of last week, we saw how you could add vectors in three very specific situations. You could add vectors if they were in the same direction, if they were in opposite directions, or if they were perpendicular to each other. Any other situation is going to require that we use what are called vector components, and that's what we're going to look at today. So we're going to start by finding components of vectors, and then we're going to actually do the vector addition using these components that we learn about. Before we actually get to that, I suppose we're going to do a bit of a review here. So far, we've looked at three different cases where you are adding vectors together. The first being that you're adding vectors together that are in the same direction. And this doesn't even really require that much of an explanation, I don't think. It says if the vectors are in the same direction, then when you add them, you simply add up the magnitudes of the vectors and you assign the direction to your answer that's the direction that they both had. So for example, if I said to you, what is the sum of this vector, 35 kilometers west, plus 55 kilometers west, the second vector, since they're both west, all you're going to do is add the two numbers together and get 90 kilometers. And since they're both west, then our answer would be 90 kilometers west. Pretty straightforward. If two vectors are in opposite directions, and again, this requires very little explanation, but I'm going to go through it in detail anyway, then you find the sum of the vectors by actually subtracting the magnitudes of the vectors, and you attach a direction to your answer that's the direction that the bigger of the two vectors had. So for example, if I am adding 35 kilometers west plus 55 kilometers, but this time it's east, I have a greater vector towards the east. I take 55 minus 35 and get 20. So my answer is 20 kilometers, and the magnitude is 20 kilometers. The direction is east because the larger of the two vectors was east. And before we go on, I'll remind you that these examples I'm using today and the ones we're going to work on today are all displacements, but these rules could be used to add any vectors, whether you were adding force vectors of newtons and newtons, or acceleration vectors, or velocity vectors. The rules are going to be the same. The third situation we looked at got just a little bit more complicated. If you had two vectors that were perpendicular to each other, then you draw the two vectors tip to tail, and you draw then a single vector from where you started drawing them to where you finished drawing them. And that vector is going to be the sum of the two vectors. So you can use the Pythagorean theorem and right-angle trigonometry to find the magnitude and the direction of that vector. For example, if I give you 35 kilometers west and 55 kilometers north, and I say add them, well, they're not in the same direction, so you cannot simply add the numbers together. They are not in opposite directions, so you're not allowed to just subtract the numbers. They're perpendicular, so we draw them tip to tail. My recommendation is always, and I don't know if you remember this from Friday, but I'll repeat it anyway, just in case you didn't, draw the horizontal vector first. So when you're looking at a map, west is to your left, 35 kilometers west, tip to tail with the north means I draw the north starting at where the 35 kilometer west vector ended. And that hypotenuse is the vector that's the sum of 35 kilometers west and 55 kilometers north. Of course, you need to find the magnitude of that, which is the hypotenuse, and you also need to find the direction, which would be a certain number of degrees. You would use the Pythagorean theorem to find the hypotenuse, so you would take on your calculator 55 squared plus 35 squared, and then you would take the square root. I'll give everybody just a second here to go through and do that calculation. So we're finding the hypotenuse of that triangle. I get 65 kilometers. Just to show that to you on a calculator, in case a couple of you didn't get it, we're taking 55 squared plus 35 squared. Then we're taking the square root of that. And I'm choosing to round my answer to the nearest kilometer, basically because the numbers in the question had 2 digits. I'm going to record my answer as 2 digits. Although, to be fair, I don't really care about the rounding today. We're in learning mode here, and I don't want to get bogged down in significant figures. The other thing we have to do is find that angle. When you go to your formula sheet, and I'm pointing this out to you because some of you might not have really good memories with regards to this stuff. On your physics formula sheet, there's actually a section called trigonometry and geometry, and you can see your 3 trigonometric ratios here. In this triangle, in regards to that angle here, 55 is the opposite, 35 is the adjacent. So what we're going to end up using is the tangent ratio. So we can write tangent of theta equals 55 over 35. You are going to have to take 55 divided by 35 on your calculator and then take the inverse tangent of that. Of course, remembering to put your calculator into degree mode or check to see that it's in degree mode, and mine is. So second tan of 55 over 35. You can either calculate 55 over 35 first and then go second tan of the answer, or you can just enter it in one shot like I have, and I get rounded to the nearest decimal. Wow, let's go to the nearest degree. Rounded to the nearest degree, 58 degrees. Please make a note that in the recording of this video, I just calculated 58 degrees, and I said 58 degrees, and 58 degrees is in fact the correct angle, but when I continue with the video in a second, I'm going to make reference to 68 degrees, both in what I say and what I write. The correct answer is 58 degrees. So we're going to record for an answer 65 kilometers at an angle of 68 degrees north of west. And that's the answer to the third part of the warm-up. Okay, now let's talk about vector components. If we're going to add vectors that are not in the same direction and are also not in opposite directions and are also not perpendicular to each other, then we need to be able to determine what are called the x component and y component of the vectors. What an x component is a single vector that's either east or west, which is telling you how far east or west the vector is pointing. If we want to talk about a vertical component of a particular vector, the vertical component is going to tell us how far north or south the original vector points. Example 1 is really kind of a warm-up here. It's a basic trigonometry problem. First of all, we're asked to draw the vector diagram for a displacement of 400 meters at an angle of 30 degrees north of east. Well, first of all, north of east means you look towards the east and then you move from east north of it. So east is to the right, north of that will be up, which means that this is a 30-degree north of east direction, and that means that this is the displacement vector that we're talking about. So take a second and draw that. It doesn't have to be perfect. You should use a ruler, but you don't need a protractor to draw that angle. You can estimate it. Now it asks us to find the horizontal and vertical components of that vector. What does that mean? Well, this is the horizontal component, and this is the vertical component. We're going to call those x and y. And essentially, when you look at those two gray vectors, when we add those two vectors together tip to tail, we get that 400 meters at 30 degrees north of east. Which means that 400 meters 30 degrees north of east can be thought of instead as a certain number of meters east and a certain number of meters north. And the amount east and the amount north are what we call the horizontal and vertical components. So how do we calculate them? Well, we're going to use trigonometry. When you take a look at this triangle, we know the hypotenuse of the triangle, we know the angle, y is opposite that angle, and sine of theta is equal to opposite over hypotenuse when you look at your formula sheet, which means if we want to find the y component, we can make use of the sine ratio, whereas since x is adjacent to the angle, when we want to find x, we can make use of the cosine of the angle. So essentially, using SOHCAHTOA from grade 10, we can write cosine of 30 degrees equals x over 400. And that's going to allow us to find x. We can also write sine of 30 degrees equals y over 400. And that's going to allow us to find y. I get x equals 346. When you're looking at this particular little equation here, the one that I'm highlighting the equal sign on, all we have to do is multiply both sides by 400 and we'll be left with x. And when you look at this equation, all we have to do is multiply both sides by 400 and we'll be left with y. So I get for y 200 and for x 346. While you're potentially finishing writing down your work, I'll just show that on the calculator up here. 400 cosine 30 degrees. Again, always make sure your calculator is in degree mode. I get 346. You know, it's 346.41 something, but I'm just going to record 346. And when I take 400 times sine of 30, I get 200 meters. So going back to the question, the horizontal component of that vector is 346 meters east. And notice I put the direction on here. In this region over here, where I say x equals 346, I'm just saying x in the diagram is 346. That's my math. When I actually say what the horizontal component of the vector is, I not only need to say 346 meters, but I also need to say east. Similarly, when I say, well, what is the y component? Well, the value of y in our diagram is 200 meters, but it's pointing to the north, so our answer is 200 meters north. And that's the answer to part B of example 1. I hope I'm leaving enough pause time in between some of these things for people to write things down. If not, this video can always be paused to give you more time. Let's take a look at example 1C. Explain the relationship between the original vector and the two components of the original vector. So I want to be very careful here. The original vector is what I'm highlighting in yellow. And the components are what I'm highlighting in green. And I'm not putting arrowheads on there. All I'm doing, everyone, is just highlighting what I'm talking about in question C. The original vector is that yellow vector, and the two green vectors are the x and y components. The point that I want to make here is that when you add those two green vectors together, you get the yellow vector. So what's the relationship between the original vector and the components of the original vector? If you add the x and y components together, you get the original vector. Another way to look at this, everybody, is if we had to work with the original vector, what we could do instead is work with the components. We could find the components, then take the original vector and throw it out, and work with the components. Another way to put this mathematically is the vector component in the x direction plus the vector component in the y direction equals the vector. Now again, these are vectors, so when I say add, I'm not saying you add the numbers together. I'm saying you take this x component and draw it tip to tail with the y component, and you will get the vector that we started off with. Okay, what we're going to do now is work through two examples where we make use of this. So let's take a look at example 2. Add the following vectors. So what we're going to do first of all is talk about those directions of 135 degrees. And there's no north of east or south of west or anything there. So I told you on Friday that when you're given an angle like that, it's what's called the rectangular coordinate system. And when you look at the XY grid, as if it's on a map, east is to the right, west is to the left, north is up, south is down, and 0 degrees is pointing east. And any direction is always rotating that brown arrow counterclockwise. So if I rotate this counterclockwise, which is in this direction, and I rotate it 135 degrees, I will get the direction of the 100-meter vector. If I rotate it 90 degrees, I will get the direction of the 120-meter vector. Well, 90 degrees is going to take me to the top, and what that tells me is that this 90-degree angle is north. So the 120 meters is simply north. If I go back to the beginning and I rotate this arrow 135 degrees, 90 degrees to here, how much further do I have to go? Well, I want to get to 135. 135 minus 90 is 45 degrees. So 135 degrees is at exactly 45 degrees between west and north. And that allows us to draw these two vectors. So the 100 meters is 45 degrees north of west. If I go back and look at this diagram, this is 45 degrees in here, so I'm just saying it's 45 degrees north of west. Is it also 45 degrees west of north? Yes, but I would prefer you to always record angles. You're going to have to think about this carefully. Record angles that are either north of west or south of west or north of east or south of east. I would prefer you to always have north of or south of as a direction. The 90 degrees, of course, is north. What this allows us to do now is draw the vectors. 100 meters at an angle of 45 degrees north of west would look like that. And 120 meters north would look like that. I'll give everybody a minute here to draw those. All right, so what do we do with them? Well, we don't really know how to add these two vectors. These two vectors are not in the same direction. They're not in opposite directions, and they are not at right angles to each other. So what we do instead of trying to add them is we find the x and y components of all of these. So when you take a look, let's talk about the 100-meter vector. It has an x component that's to the west and a y component that's to the north. If we want to find those two components, we just take a trip back in time to Math 10. You're trying to find the two sides of this right angle triangle, so you can, to find x, which is the horizontal component, use cos of 45 equals x over 100. To find y, you can use sine of 45 equals x over 100. It's not a math class, but I'm going to point out to you that cosine of 45 and sine of 45 are the same number. So I'll give you a minute to solve for x and y there. essentially all you're going to do is take 100 multiplied by the cos of 45 degrees. You get 70.7. If you take 100 times the sine of 45 degrees, well, you get the same thing. Because a 45-degree triangle and a right angle triangle is isosceles, these two sides will be equal. So that tells us that x has a value of 70.7 meters and y has a value of 70.7. However, the components need directions. So when you write the 70.7 meters for x, you need to indicate that it's west, and you need to indicate for y that it's 70.7 meters north. Now, what do we do about the 120 meters north? Well, since it's exactly north, all 120 meters of that is the vertical component, and there is no horizontal component. This vector, when you're looking at the 120 meter vector, the arrow, that arrow doesn't lean towards the east or lean towards the west. There is no east-west to it. Now, the point I want to make right now, and this is really important that you understand this procedure, is that this 100-meter vector at 45 degrees north of west, we don't need it anymore. We're done with it because what we have instead are these two vectors, which are the same as 100 meters at 45 degrees north of west. And this 120 meters north, it's not necessary either, because we can replace it with two vectors that are horizontal and vertical components. So it seems as though we've made things more complicated because we've gone from trying to add two vectors, the original vectors, and now we're adding four vectors. However, since these are all horizontal and vertical, it's very easy to add them. I can find the total x by adding my 70.7 meters west and my 0 meters, and I get a total west of 70.7 meters. Pardon me, I get a total x of 70.7 meters. If I want to find the total of my y components, I can add 70.7 meters north and 120 meters north and get 190.7 meters north. And, you know, this crossing out of the vectors that I did earlier, if you're going to do that, that's fine, but don't like cross them out so that you can't see them anymore. Just keep in mind that we're not using them anymore, but don't scribble over them so much that you can't read them. Now, we don't actually need, if you look at the board right now at the highlighted vectors, we don't actually need those two x components because we have this instead. And we don't actually need those two y components because we have that instead. So these two vectors here replace the original two vectors. We started off with these two vectors. And we broke each of them into x and y components, and then we said, let's add these four vectors instead. Then we added the x to get a single x and added the y to get a single y, and now we're down to these two vectors, which you can add by drawing them tip to tail. If I want to add these two vectors, then I draw my horizontal first, 70.7 meters west. Then I draw my 190.7 meters north. And the sum of those two vectors, which is the sum of all of my components, which is the sum of the original two vectors, is represented by this vector. And again, you need to find the hypotenuse and the angle. And to be honest, the remainder of this question, you calculating the hypotenuse and the angle, you know, that's as I like to say, that's like stealing candy from a weak and tired baby. It's pretty simple. There shouldn't really be any difficulty there. You're going to use the Pythagorean theorem to find the hypotenuse. You're going to use tangent, I would assume, by going opposite over adjacent and then inverse tan to find the angle, and I will give you just a minute to do so. Okay, I get 203 meters at 70 degrees north of east very quickly here. I think I've given you enough time. If you take the inverse tan of 190.7, you would on an exam want to carry all of your decimals, but here it doesn't really matter. The inverse tan of 190.7 over 70.7, I round that to 70 degrees, and then I can take the Pythagorean theorem 190.7 squared plus 70.7 squared, and I have to take the square root. Don't forget to take the square root. I think when you look at this answer, this 41364.98, you realize you're not done yet. It's quite large. So I get 203 meters. Hopefully everybody's caught up. If not, the video can be paused at this point to let everybody catch up. In the meantime, I'm going to move forward. So we have two displacement vectors we're going to add. The general procedure is we're going to take these vectors, replace them with x and y components for each, then look at all of the x components and add them together, look at all of the y components and add them together, and then take the total x, which is a single vector, plus the total y, which is a single vector, and add them to get the answer. So first of all, 20 degrees north of east is in that direction, so this is the first vector, and 60 degrees north of east is in that direction. This is the second vector. I'll give everybody a minute to just copy those diagrams down. Okay, so these are the two vectors. And what we want to do is look at the components of these vectors. We want to determine an x component and a y component for each of them. So let me sketch in the x and y components. And what I will tell you right now is that everything above this line in terms of finding those missing sides, the x and y components, is grade 10 trigonometry. You need to use the fact that you know the hypotenuse and the angle to find the opposite side and the adjacent side. So for example, and I don't have this typed out, I'm just going to say it verbally, if you take a look at finding the opposite side, which is y, sine of 20 degrees equals the opposite over 7, which means the opposite side will be 7 multiplied by sine 20. This is the y component of the first vector. If I take cosine of 20 degrees, that's the adjacent side over the hypotenuse. And that means that the adjacent side, which is our x, is going to be 7 cosine 20. And you can repeat the procedure for the second vector as well. I'm going to give everybody just a minute here to record your x's and your y's. Just finishing up, I will show you what I get for all of my x's and y's. You'll notice that I didn't just put the numbers of kilometers, I put directions as well. Both of these vectors are to the east and to the north. So hopefully you got all those. What is the purpose of doing this? Don't forget, what we're trying to do is add this vector and this vector. So the logic here is that this first vector of 7 kilometers at 20 degrees north of east, that vector is no longer needed because we have this x and y component which replace it. And this 4 kilometers at 60 degrees north of east, that can go in the bin as well because we have an x and a y component which when added together give that original vector. So we can use these two components instead. Now what we're going to do, same as example 2, we're going to find the total x. So I need to add the 6.58 kilometers east and the 2 kilometers east. That's pretty basic. They're in the same direction, so I add the numbers together, and the direction is obviously east. I need to find the total y. So I have 2.39 kilometers north, 3.46 kilometers north. That's pretty easy. I just add the numbers together and get 5.86 kilometers north because they're both north. And again, the reasoning now is that these two vectors up top that I've just crossed out are not needed anymore because I now have the total of them. It's 8.58 kilometers east. And these two vectors I don't need either because I know that they add together to give 5.86 kilometers north. So why don't I use 5.86 kilometers north instead? We're almost done here. All you need to do is add these two highlighted vectors together. So how do you do that? How do you add these two vectors together? Well, they're at right angles to each other, so we draw them tip to tail. Again, my recommendation is you draw the horizontal first. So that's 8.58 kilometers east. Then you draw the vertical, which is 5.86 kilometers north. The hypotenuse pointing from where you started to where you finished drawing this is the total that we're after. We need to find the length of that, which will be the magnitude of the total displacement, and we need to find the angle, which will be a certain number of degrees north of east. Give everybody just a minute here to calculate the hypotenuse. It's the Pythagorean theorem that you're using. I get 10 meters. It's not exactly 10, and I'm not going to carry all my decimals because I don't have access to them right now, but it doesn't matter. 8.58 squared plus 5.86 squared. I take the square root. It's going to be 10 point something, but, round it to the nearest kilometer. We're going to say 10 kilometers. And I do see that I have a typing mistake up here where I have 10 meters. That should say kilometers. We also want to find the direction. And I get for a direction 34 degrees north of east, just to show that calculation to you. Inverse tan of the opposite side, which is 5.86, divided by the adjacent, which is 8.58. Gives me 34 degrees, and in the diagram it's going north from east, so north of east. And again, this should say kilometers, but that is our answer. So the answer is 10 kilometers, 34 degrees north of east. Okay, so your assignment, page 88, questions 1 to 3, page 90 of your textbook, numbers 6, 7, and 8, and also number 11. I've highlighted some of that, what you're looking at on the screen, because in your handout I believe it just says 6 and 8, but I would like you to do 6, 7, and 8, and 11. I've also got a couple of additional problems typed out on page 34 of your unit handout. According to my rough watch of my time here, you should have about 40 to 45 minutes left in class. I would say to you that if you get the textbook done in class, that would be definitely what you need to have done for tomorrow. But if you are done before the end of the class, the textbook material, then you need to start working on the 2 attached problems. If you don't have a textbook, you can pick up a photocopy of these pages from the front of the room. So I hope that that lesson went well. I hope that you have a great day, and I hope to see you soon. Take care.